Ladies and gentlemen, welcome back to my Introduction to Mathematics course. In this chapter, we will get acquainted with the basic notions from logic that we need to follow and construct mathematical arguments. There are certainly many ways to explain what mathematics is, but one defining property is that in mathematics we study abstract constructs by reasoning alone. This means we take some known fact and try to deduce something else out of it, hopefully a result that was previously unknown. In mathematics, this reasoning is done by logical thinking alone, not by using real-world observations, measurements, or experiments as one would do in the sciences. And logic could be called the science of truth. It is concerned with the truth and also the falsity of statements. So we study the components that make up a statement and how its truth is determined by that of its component statements. We study relations between the truth and falsity of different statements and methods to determine it. By studying truth, logic provides us with the tools for mathematical reasoning. In this and the following chapters, we will explore the basic logical constructions for propositions and logical methods of reasoning, so-called proofs. Now, if this interests you, please take a moment to like this video and subscribe to my channel. So this way you can keep up to date with further chapters of this course and with new courses that I will produce in the future. Thank you. Here's an overview of what this chapter will be about. First, I will introduce propositions and their truth values. Then we will look at logical operations on these propositions. Then I will introduce quantifiers to get a finer version of propositions. And finally, I will briefly introduce set notation. We begin with propositions and truth. A proposition is merely a sentence that can be either true or false, but of course it cannot be both at the same time. Here are some simple examples of propositions. First one, 4 is a prime number. Second one, mathematics is an enjoyable activity. Reading is the capital of England. This video will eventually reach 1 million views, and all cats are grey at night. Now note that for some of these, there's some context required to determine whether these are true or false. For example, if we look at this proposition here, mathematics is an enjoyable activity, well, that is a statement that is either true or false, but it might depend on who is making that statement. Also with this one, this video will eventually reach 1 million views. This is definitely true or false, but at this point in time, we can probably not say if it's true or false. Perhaps one day you, my dear viewer, will see this video and will already notice that it has more than 1 million views, then the truth value will be determined for you, but perhaps this will never happen. Who knows? Also, we should note that slightly different sentences can convey the same statement. For example, this one here, all cats are grey at night. I could phrase it as, if it is night, then all cats are grey, which means exactly the same thing. And since we're here concerned only with the truth value of statements and of propositions and not with linguistic properties, we treat these as one and the same proposition. And here are some examples of non-propositions. So sentences or statements that do not have a truth value assigned to them. What time is it? That's a question. Blue is taller than cats. Go home and yabba dabba doo. So note that for none of these sentences it would make sense to say this is true or this is false. The first one is a question. The second one, even though syntactically it has the shape of a proposition that could be true or false, is a nonsensical statement, however, because blue and cats cannot be compared by the measure of tallness. So this is nonsense. So we cannot ascribe the value true or false to this statement. Now go home. This looks like an order, a command, but it doesn't make sense to say this is true or false. And with yabba dabba do, I don't even know what it is, but it is certainly neither true nor false, so it's not a proposition. When studying propositions, it can be helpful to use variables, A, B, C, and so on, as placeholder for propositions. So I want to illustrate this with an example. We have two different propositions here that share the same structure. The first one, if n is an odd number, then 2 does not divide n. And the second one is, if you drink acid, you die. They have completely different meanings, but they do have the same structure, which is if A, then B. So with the first proposition, the A part would correspond n is an odd number, and the B part would correspond to 2 does not divide n. Whereas in the second proposition, the A part corresponds to you drink acid, and the B part corresponds to you die. So the variables themselves are not true or false. It doesn't make sense to say that. So when we ask whether such an expression here is true or false, we must reason about this in a way that allows all possible assignments of true and false to A and B, to the variables appearing in it. Because we must take into account all possible propositions that we could plug in for those variables. The use of variables simplifies studying propositions, as we can study the structure of propositions irrespective of the particular meaning of the variables A and B. And next we will learn how the structure is built up. We look at logical operations. We can form so-called compound propositions out of given propositions by using these logical operations here. The first one, with this little hook symbol, is the negation. It means not, so we get a proposition and it just assigns the opposite meaning to it. The next one, with a little hat as a symbol, is called the conjunction. It means and, so we combine two propositions with an and. Then we have this V-shaped operator, the disjunction, which combines two propositions with an or. So we say A or B when we use this symbol. Then we have the implication, denoted by an arrow. So we would have A, arrow B, which we read as A implies B, or if A, then B. And then we have the equivalence, which is basically the implications in two directions. It means A is equivalent to B, or A is true if and only if B is true. So this corresponds to saying A implies B and B implies A. And just like in arithmetic, where multiplications take precedence over additions, these operators have different priorities. So we prioritize them according to the order in which I list them here. For example, if I write not A or B, then this means not A evaluated first, indicated by the parenthesis, and then what comes out here, or B. Or if I write A and B or C, because the and has a higher priority than the or, this means, in parentheses, A and B, and whatever comes out of this, or C. And we can use parentheses, as you would expect it, to change or emphasize the order of operations. So let's apply this to one of our previous examples. So by the letter N, I denote the proposition it is night, and by the letter C, I denote the proposition all cats are gray. And then this implication here, N implies C, or if N then C, means all cats are gray at night, or if I want to say it more explicitly, if it is night, then all cats are gray. So these, as I mentioned before, are just two reformulations of the same proposition, so I do not consider them as two different things. And when we use variables a, b, c, and so on as placeholders for unspecified propositions, then the expressions we obtain by applying the logical operations that we just got to know will be called formulas. Though by a mild abuse of language, I will sometimes simply refer to the formulas as propositions as well. They're just propositions where we haven't made explicit all the parts yet. And for such a formula, one can speak of a truth value once we know which truth values are assigned to their component propositions A, B, C, and so on. And this leads us to truth tables for formulas, where we cover all possibilities of what truth values we can plug in for the placeholders. If we know the truth values, which are at T or F, for true or false, of some of the basic propositions, then we can determine the truth values of the compound propositions via the following truth tables. And here I'll list them all. I'll go through them one by one in a moment. It is probably very helpful to always have these truth tables at hand when you're studying more complicated propositions. So maybe it would be good to get a copy of these or write them down on a piece of paper now and have them by your side when we are studying logic here. Okay, let's look at them one by one. The simplest one is the negation. We have some proposition A, and the negation is really just the opposite value. So we flip the truth value of A if we negate it. So if A is false, then we get true for the negation, and if A is true, then we get false for the negation. Here we have the logical AND, so we have two propositions A and B, and then we get the compound proposition A and B. And yeah, this proposition we would expect to be true if these two components are true, but if one of them is not true, then this compound statement would also not be true. And this is reflected in the truth table. If A is true and B is true, then A and B is true. But if either one of them is false, then A and B cannot be true, so it has to be false. Next we have the OR, A or B. So we again have two component propositions A and B. And we would expect the statement A or B to be true if one of the two, at least one of the two of A and B, is true. But if both of them are false, if A is false and B is false, then also A or B would be false. In all other cases, at least one of the two is true, and then A or B is true. Then we have the implication. A implies B, or if A then B. Now, this is a bit delicate, probably the least intuitive one. First, let's look at the case that A is true at the last two rows here. So the statement is if A then B. That means if A is true, then B should be true. This is the claim made by this formula here. So if A is true and B is true, then this claim is true. Then it is correct that A implies B. So this is true. However, if A is true, but B is false, then we cannot say that A implies B. It contradicts what we understand under A implies B. So if A is true and B is false, then A implies B should be false. Okay, now what is the case if A is actually false? Well, if we say A implies B, which means if A is true, then B is true, this doesn't make any claim about the case that A is false. So if A is false, we do not have any claim here. So A implies B is certainly not false. But if it's not false, then it has to be true. And that's why we assign the truth values true to the situation when A is false, regardless of what the value of B is. And finally, we have the equivalence. A is equivalent to B. So this is the claim that A is true whenever B is true, and that also B is true whenever A is true. And this is reflected in the truth table here. It is always true when A and B have the same value, and it is false if they have different values. Let's look at some examples for the logical operations. First, the simplest one, the negation. So here I have a proposition that happens to be false, which is A equals 4 is a prime number. And when I negate this, I get not A, which translates into 4 is not a prime number. So our original proposition is false because 4 isn't a prime number, but if we negate it, then not A becomes a true proposition. Next, we look at the conjunction and disjunction, so the and the or. And I'm given two propositions here. A equals 4 is a prime number, same we had before, and B, 3 is a prime number. Now again, the first one is a false proposition and the second one is a true proposition. And then we can combine them. So A and B, 4 is a prime number and 3 is a prime number. That amounts to saying that both of them are prime numbers, and that is not correct because we know 4 is not a prime number. So A and B is false because one of the two component proposition, in this case A, is false. However, if we look at the or, A or B, 4 is a prime number or 3 is a prime number, here it is enough that one of the two is a prime number to make this statement true. And since 3 is a prime number, the overall statement A or B is correct. It is true. Then the implication in an example. So I have two statements here. A, it is raining, and B, the ground gets wet. And by rules for the implications, A implies B, which means if it rains, the ground gets wet, is true whenever B is true. And moreover, this means the implication is true if A is false, regardless of what B is. And this is what I just talked about when we looked at the truth table. And yes, this may seem a bit at odds with our intuition, but firstly, from a purely formal point of view, it is necessary to have this in order to distinguish the implication from the equivalence. And as I said before with the truth table, if you consider what this implication means and if A is false, then we actually do not make any claim at all on how A and B are related. So we cannot say that A implies B is false then, so it has to be true. But if B is false and A is true, then the implication A implies B must be false. So that would be the case if it is raining, but the ground does not get wet, then the implication that it gets wet when it rains is false. So this could be the case if you're in a house and you're protected from the rain, then you would have this situation where it does rain, but the ground does not get wet, so it would be false to say that the ground gets wet if it rains. Now an example for the equivalence. Here we have the two propositions A is 4 is a prime number and B 3 is a prime number, the same ones we had before. And the equivalent proposition would be A equivalent B, 4 is a prime number if and only if 3 is a prime number. Now that's not a very sensible statement, but we can construct the proposition in this way and we can assign it a truth value. And in this case, this is false, so A and B are not equivalent because A is false and B is true. And now I want to look at an example where we combine more than two propositions. So we have three propositions here. N, it is night. C, all cats are gray. And R, it is raining. And we can form two compound propositions from these using the same operators, the and the implication, in the same order. But we use parentheses to change the priority on how to interpret these components. So let's translate these two formulas into propositions. The first one is N, and in parentheses R implies C, and the second one is N and R in parentheses implies C. So here we have it is night and if it is raining, then all cats are gray. And compare this to the next one. If it is night and raining, then all cats are gray. So if you think about it intuitively, that should be two different meanings. And if it's not clear from the outset, we can use truth tables to confirm that these are really two distinct propositions. So I skipped over a few steps when I wrote down these truth tables, but let's quickly go through it. So here we have the three component propositions, N, C, and R. And here I have the corresponding values for the two compound propositions, depending on every possible input combination for N, C, and R. And I will just quickly reason how we come to these outcomes here. So for this one, note that it is false whenever N or R implies C is false. So in every row where N is already false, this one is false. In the other rows, N is true. So in order to check if this statement is this proposition is true, we need to check if R implies C is true. And what we just learned about the implication R implies C is only false if R is true and C is not true. So that would be this row here. So we assumed N to be true, and then R is true and C is false. Then this bit is false and we get a false value here. And in all other cases where N is already true and R implies C is not this combination here, we get true as a result. And now we compare this with the second compound proposition, and we already see it's something completely different in the truth table here. So how do we get this one? What we have up here is an implication. Something implies C. And again, we say this is false only if C is false and whatever is here, this something, is true. Now, this one, this something, is true precisely if both N and R are true. So we need to look at the rows where N and R are both true. That's only the last two ones. And out of those, when those two are true, this part in the beginning here is true. And only if C is false do we get the outcome false here. That's only the case in the next to last row. So we only get one output false in this truth table, and in every other situation it has to be true. So by comparing these, we see that the truth tables of these two compound propositions are very different, so they are not the same proposition. And this comparison motivates the notion of equivalence. So first we say two propositions are equivalent if they make identical claims about the state of the world. And this is an awfully philosophical definition, but we do get something more tangible if we look at formulas. So first, I call a formula a tautology if it assumes the value true for every possible choice of truth values that are assigned to its component propositions. Okay, so if I write down the truth table and I always get true no matter what the input values are. And then, with this idea of a tautology, I say two formulas, F1 and F2, are equivalent if the formula F1 equivalent F2 is a tautology. In practice, that means if we are given two such formulas, we can check their equivalence by verifying that they have identical truth tables. So we take F1 and F2, write down their truth tables, and if they're identical, then we know F1 and F2 are equivalent. So I want to illustrate this with examples. First, an example for a tautology. Here I have the proposition, or the formula to be precise, A implies the negation of B and not A. I write down the truth table, so I already did it here. Let's go through the steps. So here we have all possible combinations of truth values for A and B. And then first I look at this part here, B and not A. And by using the truth tables we know, this has to be true precisely if both parts here are true. This means B has to be true. And this is true precisely if A is false. So this is only true if A is false and B is true. Thus we get this column here. And negating this, so looking at this part here, it simply flips the truth values. So by flipping these values here, we get not, in parentheses, B and not A. And now we have this right-hand side for our implication. So we have A implies blah, blah, blah. We have the truth table for blah, blah, blah. So looking at the truth tables for the implication, we find that A implies blah, 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 is always true. Okay, remember this implication, A implies something, is only false in the case that A itself is true and this something is false. Now the only case where something is false requires A to be false. So we never have the situation where A is true and the right-hand side is false. So it has to be true all the way. Okay, and now we've seen a tautology and we want to see an equivalence as well. So we use truth tables to show that the formula A equivalent B and the formula A implies B and B implies A are equivalent. So I already mentioned that before, that this is what we intuitively expect from the meaning of the equivalence, but let's verify this formally with truth tables. First, I investigate the two components of the right-hand side formula. So here again, we write down all possible true-false combinations for A and B. And then just by looking up the truth table for A implies B, we get this column here. And we do the same for B implies A, just with the roles of A and B reversed. So we get this column here. And now we can evaluate the whole right-hand side, A implies B and B implies A. We know the truth tables for these two. So the AND of those two components here is true whenever both of them are true, and otherwise it's false. So we get this column here. So here we have true, true, giving a true here, and in the bottom row we also have true, true, yielding a true here, and in the other two cases we have a false. So we have false in the AND of these two parts. And now we compare this with the truth table for the equivalence. We know that already, we had it before. So yeah, we see they are indeed the same. So this proposition here and this proposition here are indeed equivalent. They have the same meaning. And now we take a short break for you to practice what you just learned. So pause this video for a few minutes and use truth tables to show that these two formulas are equivalent. Not A or B should be equivalent to A implies B. Did you really pause the video? Seriously, give it a try. If you don't know what to do, just rewind the video and look at the truth tables again. Look at the previous example again, how we did it there, and try to emulate what we did. All right, I hope you took some time to try it yourself. So let's take a quick look at the solution. And please compare it with your own way. Here we have all possible combinations of true and false for A and B. And the first thing I do, I write down the truth table for the negation of A. So I simply flip the truth values in the first column, getting this one. And then I use the truth table for the logical OR to set up the truth table for not A or B. And I get true, true, false, true for this one. So this should be true whenever one of the two components is true. That means whenever B is true, corresponding to these two rows here. Or if not A is true, that means when A is false. So the only way we get a false here is if A is true, turning this not A into a false, and if B is false, then we get the false here. And now if we compare this with the truth table for the implication, we see, yes, indeed, they're the same. So logically, not A or B has the same meaning as A implies B. Next, we refine our notion of a proposition by introducing predicates and quantifiers. If we generalize propositions by allowing them to depend on yet indeterminate variables, x, y, z, then we obtain predicates. So here is an example. The predicate P, depending on a variable x, is defined to be the proposition x is a prime number. And this depends on x. Now, Px is true if x is equal to 2, because 2 is a prime number, but it is false if x equals 4. because 4 is not a prime number. Now, please be careful not to confuse this with the variables we introduced earlier to stand in for full propositions. The variable appearing in a predicate represents only a single value, not a full statement. It does not stand for a full proposition, as we had it before in the logical formulas, but here it just represents a single value. As the example shows, it makes no sense to talk about the truth or falsity of a predicate per se. To obtain a proposition from a predicate, we either have to fix a value for the variables in it, as we did right here in this example, where we plugged in 2 or 4 and got 2 different propositions out of it, one of them being true, one of them being false. Or we have to quantify the range of the variable's values that can appear in the predicate. And to quantify the variables in a predicate, we use quantifier notation. And we have 2 quantifiers, the first being the universal quantifier, denoted by an upside down A, which states that Px, the predicate depending on the variable x, holds for all possible values of x. So we write it down like this: for all x, Px, which means for all values x, the statement P of x is true. And it has to be clear from the context here what the admissible values for x are, so which values we can plug in for the variable x. Now just a side remark, this colon here is just an auxiliary symbol that I use to enhance readability, and it has no meaning for the logical content of the proposition. Okay, so it's just for easy reading. Our second quantifier is the existential quantifier, which is a mirrored E, and it states that P of x is true for one value x at least. So we write it as there exists an x such that Px, there exists x for which the statement Px is true. And predicates can have more than one variable on which they depend, and if our predicate depends on n variables, x1 to xn, then we have to use n quantifiers, one for each variable, to obtain a verifiable proposition. We have an example here. So consider the predicate P xy, so depending on 2 variables x and y, which says that x is smaller than y. And we assume that x and y are natural numbers. So let's form a quantified proposition. We have 2 variables, so we need 2 quantifiers. And I use this one here. For all x, there exists y such that P xy. And this means for all x, there exists a y such that x is smaller than y. Now this is clearly a true statement, because for the natural numbers we can always find one when we are given x, any x, we can find one that is larger, so then x would be smaller. For example, we can just pick the next number, we choose y to be x plus 1, and then x is smaller than x plus 1, and that holds for all x. So this is a true proposition. So with this example, we can also observe that in general we cannot change the order of the quantifiers. So if you look at this proposition here, which uses the same quantifiers as we had up here, but we reverse the order, then we see this. So this one means there exists y such that for all x, Px, y, which translates into there exists y such that all x are smaller than y. And this is not true, this is a false proposition, because for any y we can choose x equal to y, and this value y would not be smaller than itself, so it cannot hold for all x, regardless of which y we chose. So this proposition is false, but with the reversed order of quantifiers, it was a true proposition, so we see that the meaning does get changed when we change the order of the quantifiers. Let's look at another example where we can practice negating quantified propositions. So here I have the proposition, the predicate Rx, stating the road X leads to Rome. And we can form the quantified proposition for all X, Rx, meaning all roads lead to Rome. And the negation of this is that there has to be at least one road that does not lead to Rome. So the negation is there exists an X such that not Rx. And what we see here, what happened, when we negate this statement, this proposition here, we flip the quantifier from an universal quantifier to an existential quantifier, and then we negated the statement behind the quantifier. And this is a general rule that can be applied mechanically. So if we negate the proposition for all x px, this is the same, this is logically equivalent to there exists x such that not px. And if we negate the proposition there exists x such that px, then this is equivalent to for all x not px. Okay, so we flip the quantifier and we pull the negation behind the quantifier. That's how you negate quantified propositions. So here I have another example for the negation of quantifiers. I just made up this abstract proposition here of the form for all x, for all y, there exists z such that px and not q, y, z. And if I want to negate this, I put the whole proposition here in parentheses and put the negation symbol in front of it. And then I apply the mechanical rule for negating quantified propositions for each one of these quantifiers here. So first I think of the part in the parentheses as a proposition of the form for all x, something should hold. And then I flip the quantifier for all x, turning it into there exists an x, and I move the negation past the quantifier. So I have there exists an x for which the negation of something should be true. Okay, and now I repeat the whole procedure with the remaining proposition inside the parentheses. I flip the for all into an existential quantifier and I move the negation past it. So now I have there exists x and there exists y for which the negation of this remaining bit here should be true. And I do the same thing with the remaining last quantifier. I flip the existential quantifier into universal quantifier and move the negation past it. So I'm left with there exists x, there exists y, such that for all z, not px and not qyz should hold. And now I can apply some rules here. The not parentheses px and not qyz becomes not px or qyz. So we've seen the negation of this quantified proposition here is ultimately equivalent to this one. Again, it's time to put your new knowledge into action. So here I have another exercise for you. Pause the video for a few minutes and solve these two little problems here. The first is look at the proposition every decision creates discontent and negate this statement. And the second part is to do this in a more formal way. So we write the following predicate D, depending on two variables x and y, which states x is discontent with decision y. So the variable x is some person and y is some decision. And now use this predicate D and the quantifiers to express this statement here in a formal logical way, and then negate the formula you found. And if you're unsure what to do, rewind the video and look at what we did in the previous examples. Okay, so I hope you did the exercise, and here's my solution. Be sure to compare it with your own. So the negation of every decision creates discontent is there's one decision that everybody is content with. Okay, so if not every decision creates discontent, at least one decision must exist that does not create discontent. So in other words, that everybody is content with. Now, the original expression here can be formalized as for all y, there exists x such that dxy. Okay, for all decisions y, there exists one person x such that x is discontent with y. The negation, formally, not for all y exists x such that dxy, and we flip the quantifiers here and move the negation inside. So this becomes there exists y such that for all x not dxy. So there exists a decision y such that for all persons x, it is not true that x is discontent with y. Now we take a first brief look at sets, mainly to get acquainted with the notation, and this will help us reason more clearly about propositions. So consider the proposition for all x, x greater or equal to 0. And without further context, it's not possible to tell whether this is true or false. For example, if x takes values in the natural numbers, this is true. But if x takes values in the integers, it is false. So natural numbers being the numbers 0, 1, 2, 3, 4, 5, and so on. And the integers including also the negatives of these natural numbers. So for the integers, this would not be a true statement, but for the natural numbers, it is. And especially when using quantifiers, it is often helpful to precisely express which objects x are included in our statements and which ones are not. And to this end, we introduce sets following Cantor's naive set theory by his original definition. A set is a gathering together into a whole of definite, distinct objects of our perception or of our thought, which are called elements of the set. This is a bit fanciful, but essentially it means that a set is a collection of objects without any additional structure, where objects do not appear twice or in any particular order. And we have a notation for sets. So if x denotes a certain set, then we can write it explicitly by using curly braces enclosing the elements of x, where we can either list the elements explicitly, such as here, x equal curly brace 1, 2, 3, 4, and the closing brace, or we can write it through logical expressions by saying that x contains all the x which satisfy the condition behind this bar, so which satisfy the condition x being greater or equal to 1 and x being less or equal than 4. So this expresses exactly the same set, but through a logical condition rather than explicitly listing the elements of the set. And if x is an element of a set x, then we write this x element, so little x element of big X. And if it's not an element of x, then we use the same symbol but crossed out. So here this means x is not contained in the set capital X. And some people think this is a euro sign. It is not. I believe it's supposed to be a stylized E for element, which would make sense. It has nothing to do with money. The most important sets we will be studying in this course are number sets. And these are probably already familiar from school, but I will just recall them so we got the terminology and notation straight. So beginning with the natural numbers, denoted by this fancy n, is just the number 0, 1, 2, 3, 4, 5, 6, 7, 8, and so on to infinity. Next up are the integers, denoted by the letter z, which is the natural numbers together with the negatives. So we don't just have 0, 1, 2, 3, 4, 5, and so on. We also have -1, -2, -3, and so on down to minus infinity. Then we can form fractions out of the integers, which gives us the rational numbers, denoted by the letter q. So these are fractions pq, where p and q are both integer numbers, but q, of course, should not be 0, because we cannot divide by 0. And then, a bit abstractly defined here, the real numbers, they are given by the continuous line of numbers that contains the rational numbers, the integer numbers, and the natural numbers, and everything in between the rationals as well. So this is a rather vague definition, and much later in this course we will actually see how the real numbers are constructed out of the rational numbers. But sets can contain pretty much anything, and very often in mathematics we have to study sets that are not sets of numbers. For example, a very important, even though very simple set, is just the empty set. It is denoted by this slashed out letter O or 0. I guess it's just supposed to be a circle in the Venn diagram notation that has been cancelled, meaning it doesn't contain anything. The empty set is the set that does not contain anything. So we can also write it as two curly braces with nothing in between them. Then, for example, we can collect the playing card suits into a set. These are not numbers, it's just a bunch of symbols, and it's perfectly fine to form a set out of them. We can collect people into sets. Alice, Bob, Claire, Dave, and Eve. Just 5 randomly selected people, or rather names of people, if you want to be very precise. So they are not numbers either, just some names. Now, other sets that are maybe more interesting for mathematics are geometrical operations. So here I say the set R index alpha is the set that contains all rotations in the plane about some point, but the rotation has to be by the angle alpha that is given in the index here, and alpha is fixed. So that means for every value alpha between 0 and 2 pi, we actually get a different set R alpha. So R0 would just be the rotation by the angle 0 degrees, so not doing anything at all. And R pi would be the rotations about the angle pi. at arbitrary points in the plane, and that would be quite a different set from R0. Next, the set of prime numbers. So these are numbers again, but not just a full number set, just a subset of the natural numbers. So I write it here, p equal to the n element of natural numbers, such that n has no divisors other than n itself and 1. And I use this first notation to mean this actually. So I can also state this as the prime numbers are those n that satisfy n being a natural number and having no divisors other than n itself and 1. But very often one moves statements like this right in the front of the set declaration to make it a little bit clearer. And finally, a geometric set again, the points on a parabola in the xy plane. So the set is called AC, index C, and it's the points with two coordinates x and y, where they satisfy this relation, x squared plus c equal to y. And here c is some real number that is fixed. And similar as we had it here with the rotations, for every number c that we choose here, we get a different set. We get a different parabola, so there are different points on different parabolas. So for every c we get a different set here, because the equation that has to satisfy it by the points in this set changes if we change c, so we get different sets. And that brings us to the end of this chapter in our Introduction to Mathematics course. And later in this course we will revisit sets and cover them much more extensively. And up to now we have learned enough about sets and logic to formulate mathematical problems, and we can now look into the methods of proving new propositions in mathematics using what we have learned so far. And this will be the content of the next chapter. So please don't forget to like and subscribe, and I hope you enjoyed this video.